Hey everybody! So I just participated in CodeChef's January Cookoff for 2021. I'm actually in Div 2 because I'm a 4-star coder, and I just finished all the problems about half an hour ago, so figured I would jump in and just explain some of my solutions and thought processes. Um, so we can actually start with, I'll start with the div 3 problems. There's two div 3 problems, these two that are not in div 2. And I haven't solved these yet, so I'll just go through these two problems and just live solve them. And then after that, I'll go and talk about each of my div 2 solutions. So here's the first div 3 problem. So you need to make a password, and there's a bunch of conditions here. It has to contain at least one lowercase letter. Okay, one uppercase letter strictly inside, not the first or last character. One digit strictly inside. One special character strictly inside. At least 10 characters in length, but can be longer. Okay, you get a bunch of passwords, and you need to check if they're good or not. Okay, this problem is kind of annoying. You just have to implement everything that they describe. Okay, let's just see if we can get this out of the way quickly. So, yeah, basically, just read in the string. And then, yeah, so first of all, there's something called isLower, which is nice. So if either the first or the last character are not lower, then we have a no and we can quit. And so that checks all this strictly inside stuff. I guess we can do this too. If the size is less than 10, then it's a no. And now we're just going to check that each of these shows up. So I guess we'll just have 4 bowls: lower, upper, digit, and special. And then for every character in S, if is lower, we're going to set lower to true. If it's upper is true. If it's a digit, digit's true. Otherwise, special is true. Because, right, these are the only things allowed here. And yeah, and then we're just going to check if all of these are true. Digit and spelled it wrong. If so, it's a yes, otherwise it's a no. So let me just run this real quick. No, no, no. So everything was a no. And why is that? Oh, I misread the problem. Okay, so it's not that the outside things have to be... Oh, I see. Okay, so it's not that the outside things have to be lowercase, it's that we can only satisfy upper, digit, and special, these conditions, by checking the inner stuff. So this is still good, but for the upper, digit, and special cases, we need to check the inner part of the string. Okay, so now I think we're good. Oh, I'm not allowed to submit this problem. Okay, so we'll just pretend that this code works. Okay, and then for this problem, this is the second problem in div 3. You're given a range of integers L, basically L through R. X is said to be reachable if you can represent it as a sum of 2 not necessarily distinct integers in this range. Find the number of distinct reachable integers. Yeah, so basically the smallest thing we can get is L plus L. The biggest thing we can get is R plus R. And then the question is, what can we get in between? And we can get everything in between. So the way that you can see that is like, you have L plus L, then you have L plus 1, L plus 2, all the way to L plus R. And then you can start increasing the left thing instead. So basically I made a list where the first number is L plus L, the last number is R plus R, and in between everything just increments by 1. And so that just shows that we can get every number in between. So then in that case, the answer is just going to be 2 times R minus 2 times L plus 1, because that's the number of integers in this range. Okay, so that's it for the div 3 problems. So now we can look at the div 2. So the first problem in div 2 is prime tuples. And here, what we have is that a tuple ABC is considered good if it consists of 3 prime numbers A, B, and C, where A is less than B is less than C, and C is less than or equal to N, and also A plus B equals C. Basically, you're given N, find the number of good tuples that you can form. So N goes up to 10 to the 6, so that's an important thing to note, and there can be a lot of different test cases. But the key thing is just looking at this problem, what you realize is most prime numbers are odd, right? Everything except 2 is odd. And in general, odd plus odd equals odd doesn't work. So if we're going to make A plus B equals C, then something has to be even. And the only thing that can be even is you can have a 2. And since 2 is the smallest prime number, it has to be A. So A has to be 2. So the only way that this can work is if basically B plus 2 equals C. And so you're just looking for pairs of primes that are 2 apart. And now that we know that, then we're just counting how many, essentially, pairs of primes up to n are 2 apart. Since n can go up to 10 to the 6th, you can actually just pre-process everything, find all the primes up to 10 to the 6th, and then find the counts for all the n. And so that each test case, you're just like reading the number and printing out from your answer array. And so that's what my code basically does. This is like pre-written prime civ code. And yeah, it's just basically pre-processing. This doesn't even need to be here, I could just go here. Okay, so yeah, we have this nmax for 10 to the 6th. We sieve that, so we find all the primes. And then answers n is basically just answers n minus 1 plus whether or not both n and n minus 2 are prime. So I could also like write it like this. So this is kind of like a prefix sums thing, where answers n is just everything before that plus whether this particular pair works. In this case, I guess I don't want to negative index here, so I should start from at least 2. And then everything else will default to 0, which is fine. So that's how we solve this. Let's go to the next problem. So maximize islands. I thought it was funny that this problem code is like min islands. Not sure what they're trying to say there. But anyway. Yeah, so you have a grid, n by m. It's only up to 10 by 10, and every cell is either water or land. And you want to, you have this definition where a group of connected land cells that are side adjacent is called an island. And you want to set up the grid so that you maximize the number of islands in it. And the thing you can do is you can take any cell and flip it from land to water or vice versa. And you want to do the min number of flips. So basically, if you analyze it, it turns out there's only up to 2 options that you can do. So if n times m is even, then you have, let's see, yeah, your options basically look like this. Or you can do kind of the negation of that. So you can do this. And both of these get a max of, in this case, 6. The reason that you know that this is a max is because you can just think about how adjacent cells have opposite parities. So if you have two neighbors, then their R plus C is going to be opposite parity. So one will be odd and one will be even. And that's kind of a way you can just convince yourself that half is the most you can do. And then in the case of n times m being odd, then there's only one option, which is to get basically all the corners and do this alternating thing in between. And so these are actually the only options to get the max number of islands. So you basically just check the input with the min difference from these options. So the code looks like this. Basically, you read the grid, and then if n times m is odd, you only have one option. Otherwise, you have two options. And then you just get the cost here and you check that. Okay. Yeah, so I'm kind of intentionally not going into super detail, just explaining like the high level ideas for like a shorter explanations video. So, okay, let's look at the third problem of div 2, which is Mex Subsequence. So you're given an array, you want to find the number of ways to divide it into contiguous subarrays such that basically every element is in exactly one subarray, and the mex of every subarray is equal to m. The mex is the smallest non-negative integer which doesn't occur in the sequence. So the first observation here is if any number occurs in your array, then it can't be m. So we're thinking about what are the possible options for m, where we make the mex of every subarray equal to m. But if a number shows up in your array, it can't be equal to m. Like m cannot be that value. For example, for this array, there's no way we can have m equals 2 because there's going to be some subarray that contains this 2, right? It might be 2, 3, it might be 1, 2. It doesn't really matter what it is, but it contains a 2, and so the mex of a subarray can never be a value that's in the subarray. And then because of that, well, what are the possible values for m? Well, m has to be a value that doesn't occur in the array at all. And if you think about it more, in fact, it's the smallest value that doesn't occur in the array at all. Because, if you think about, for example, this array, 0 and 1 both occur in the array, and then 2, 3, 4, and so on do not occur. But there's no way you can get a max of 3 or more when you don't have 2. So your goal in that case, the only option you have is to make every mex equal to 2. And so in that case, you just need to make sure every subarray contains everything less than 2 at least once. And then it just becomes kind of a standard DP problem. The way that I implemented it is I have this kind of data structure that uses PBDS priority queue. The point here is just that we can track the, out of all the numbers 0 through m-1, we can track which one was seen the longest time ago. And that's kind of telling us how far back we need to go. So for example, if m is going to be equal to 3, then we have something like this. I guess actually what I want is, yeah. Okay, and now we're considering a DP state at the end of this array. We want to know how far back the end subarray needs to go. Well, because we need to hit all of 0, 1, and 2, if we start from here, we got 0, we got 2, 2 again, 0 again, and so on. We need to go to at least here, because that way we get a 1, and we can make the mex 3. And then we can go further than that if we want. But this is the latest start point that we're allowed to do. So we can do anything from here to here. And so that's why I have this data structure. And beyond that, it's just like a relatively straightforward DP where you DP on a prefix, you count the number of ways to fill out that prefix with subarrays, and then the transition here is the DP state for this end is going to want to add the DP state for everything starting from this 1 to the left. So you also want to track DP prefix sums. So that's what I do in my code. Yeah, basically find m, special case for m equals 0. It's just 2 to the n minus 1 because you can decide whether to chop it or not chop it at every dividing point. Otherwise, you do the dp and dp something. This is the data structure. And yeah, basically that idea. So the dp value here is just the dp sum of the min of the data structure. And that's the rough idea. All right, let's look at not too colorful. So we have 3 more problems in div 2. So for this problem, oh, what happened? Okay, for this problem we have an n by m grid again, and we want to color everything. So R of the tiles needs to be red, G of them needs to be green, B of them needs to be blue. And we need to set it up so that for each tile, out of all their neighbors, there's at most 2 distinct colors. So this is an example. This works because, for this red tile, out of these neighbors, there's only 2 colors, which are blue and green. For this tile, there are only 2 colors, which are red and blue. For this tile, there is only 1 color, which is blue, which is also fine. You're just not allowed to have all 3 colors among the neighbors. So n and m are up to 500. R, G, and B can be any combination as long as they add up to the right amount. And then they also mentioned it can be proven that any solution, or that a solution always exists. So that's a pretty important thing here. Something worth digging into to figure out why that's true. Basically, that's what you need to do in this problem. Figure out why is it true that it always exists. And if you can do that, you can probably figure out how to build it. So the key thing to think about here is, for a cell, what properties are true about its neighbors? And one key thing is the parity thing that we talked about earlier, where if you have 2 neighbors, their parity of R plus C, like their chessboard or checkerboard color. So let's take a sample chessboard. Like this. The color of 2 neighboring cells will always be different. And another thing is that means that for any cell, all of their neighbors will have the same color. So for this white cell, all of the neighbors are black. And can we use that here somehow? So the way we would want to use that is if both colors only have both like white and black colors only have 2 different colors out of red, green, blue, then we're going to be good for sure, because there's no way to have 3 different colored neighbors, because all your neighbors will be from the same half of the white squares or the black squares, and that way we know it's good. If we guarantee that out of the white squares there's at most 2 colors from red, green, and blue. Out of the black squares we also guarantee there's at most 2 colors from red, green, and blue. And yeah, it turns out you can always do that. Basically, the way you do that is you kind of want to cut the 3 colors into 2 halves in a way where each half only gets 2 of the colors. So the only bad case is like for example, if we like just list out how many of each color we have. If we just have like a lot of these, so I think I'll just make 40. So this is 40. And then if we wanted to cut in half, that would be right here. And so the problem here is that, this half is fine and has all of 1 color actually, but this half has 3 different colors. And that's a problem. So we just want to cut the colors in half so that neither side has 3 colors. And if you think more about this example, the right way to do this is basically put the color that shows up the most in the middle, and then we're good. We cut it there, and then both sides get only 2 colors. The reason this is good is because the color that shows up the most will definitely cross the halfway point. because if it doesn't cross the halfway point, then what that means is, something like this, and then we have this, right? But then we have a problem because that actually means that G shows up more than B. So by putting the color that shows up the most in the middle, we're guaranteed that we cross the halfway point. Yeah, so that's all I did here. Here's the implementation. Basically just reading RGB, and then I just did kind of a manual shuffle until G is the biggest. And yeah, just do that insert here to make sure G is the biggest. And then you just kind of, I'm just going through the grid first, first do maybe like the black squares, and after that do all the white squares and just fill in the colors. And then that's it. And then this part isn't actually necessary, but this is just a quick check that the solution does actually work. You just insert all your neighbors into a set and make sure the neighbor's size is at most 2. Okay, so yeah, like I said, just trying to give high-level overview, not going like too in-depth with these solutions, just trying to, explain them relatively quickly and make a shorter video. So we got 2 more problems here. Now we're getting to the harder problems in Div 2. Although this is actually quite a big drop here already. So Mex Sub, yeah, that makes sense. Mex Sub is quite a bit harder than Maximize Islands. You need to do, you need to make some observations. You need to do DP. You need to do prefix sums. It's like several things going on. And then this one, definitely just like a tricky kind of coloring mathematical argument problem. But anyway, let's look at the last 2 here. So we have prefix and. So in this problem, you have an array, A1 through AN, and you can arrange them in any order you want. And you're going to get a score. Your score is the sum of the bitwise and of every prefix. And the way you do like multiple numbers is you just you can just reduce them 2 at a time. So one example is and of 7, 3, and 5 is 1, because basically if you write out the numbers in binary, 7 looks like this, 5 looks like this, and 3 looks like this. So the only place where they're all 1s is the 1 bit. So that means the and is 1. And yeah, so you're getting this sum of ands for all the prefixes, and you want to maximize that. And then the key thing is n is at most 2 to the 20, ai is between 0 and n minus 1. And okay, so if we think about the ands from left to right, they start with more 1s, and then they gradually lose their 1s, right? So if we think about it like this, there will be some there'll be some out of this, and then we'll lose some bits when the next number doesn't have a 1 in those bits. And maybe we'll have this for a while, and then we'll lose some more bits, right? And then maybe we'll lose some more bits, right? So if this is the list of prefix ands, it'll look something like this. And finally, eventually we'll get to the end of the array, which may or may not have any 1s, but either way, we're just going to take the sum of all these values, and that will be the answer. So yeah, so what we're actually doing is, we can think about it as we're starting from this bit mask of all 1s. It'll show up some number of times, and then we'll remove some bits, and then that will show up some number of times. We'll remove some more bits, that'll show up some number of times, and then all the way down. And so that way it's kind of like, we're kind of doing like maximum path from the all 1s bit mask to the all 0s bit mask. So each of these has some frequency. So in this case, this one is times 4, this one is times 3, this is times 1, times 1, times 1. And for this one, maybe if the and of everything is this bit mask, then this might have a frequency of 0. So the way that I solve this is basically you read all the numbers. B is just the number of bits that we need. We take a frequency of all the bits, and then I use this thing called supermask sums, which is the reverse of submask sums. It's this somewhat well-known DP technique to compute. Basically, for submask sums, it's for every mask, you want to get the sum of values sub, where sub is a submask of mask. So this is also known as sum over subsets. So basically, if mask is like 101, you want to get the sum of values 101. These are in binary, by the way. Plus values, 100 plus values 01 plus values 000. And the way that this works, it's kind of like it's like a broken profile DP, where you just kind of go through each bit one at a time, and for each bit you add the sum without the bit to the sum with the bit. And so yeah, you can just search sum over subsets, I think, if you want to look for details about that. This is just kind of a base algorithm that I'm starting with. And then there's the opposite, which is supermask sums. So you get the sum of, instead of every submask, every supermask. And it turns out the implementations for this is super easy. You just reverse, and then you do submask sums, and then you reverse again, and then you're good. So yeah, so I start with this super frequency. What that tells me is, for example, if I have this mask, how many of my numbers in my array have ones in all these bits? They can have ones in other bits, but they're not allowed to have zeros in any of my 1 bits. They have to be, their AND has to get me at least these bits in some sense. And then we're going to do this DP for all of the masks, where the idea is kind of like what we're describing here. We're going to start with the all ones and then gradually get to the all zeros. Each step, we're just going to remove 1 bit. So here I kind of like did an extra jump here when I removed 2 bits at a time. But we can think of it like this, where there's an intermediate step with a frequency of 0. So yeah, so what happens is you just solve each mask in increasing order, and then for each bit we try removing it, and that option gives us basically a super frequency of mask. That is the number of times we will have this particular bit, and so we're multiplying by 2 to the bit, and that's why we're just left shifting here. And then after that we do DP with that. So it's kind of like, in this case, we're adding this bit 4 times, and then we're getting the DP value for this state, this bit mask. And so note that, like, yes, these other bits occur 4 times, but they'll be accounted for when we solve the DP state for this bit mask, because this bit mask will also count these 4. And that's why we do the super frequency. And so that's the answer. So pretty short code in the end. You just have to think through kind of this process and then the DP state there. Okay, so yeah, in the theme of just moving along quickly, we'll go to equal gifts. So this was pretty weird because I read it, and at first it sounded like it was not solvable, but anyway, we'll just go through it here. So even though Christmas was a long time ago, we have a pile of n unopened gifts. We know the value of each gift, and we got to distribute some of them to Alice and Bob and give the rest away to charity. And there's some different rules that we need to satisfy. So first of all, they have to at least each get 1 gift. There's no sharing, and they have to get an equal sum of values of their gifts. So I guess they're very picky and competitive kids, where they'd rather both get less but get the same amount rather than both get more. But okay, anyway, given these picky kids, we gotta figure out how to distribute it or say it's impossible. And then here's the thing that's kind of crazy. So the AI is up to 10 to the 8th, and n is up to 10 to the 5th. So these are really big constraints, and the most obvious solution here is something like just a knapsack for which subset sums are possible. And that is clearly no good here because these numbers are just way too big to handle that. Okay, and yeah, so either yes or no. So just to go through examples, this case 32452, this is a yes because according to this output, we can give this 2 and this other 2 to Alice, and we can give this 4 to Bob, and they both have the same sum of 4. And then the 3 and 5 are going to Charity, so that's why they're n's. I think it would have been a little clearer if they made this a C, but anyway. And then for this example, the answer is clearly no, because there's no way to get an equal sum. The only thing we can do is, do a 10 on one side and a 70 on the other side, and that's just not equal. Okay, so how do we handle these huge constraints? So basically I was thinking about this, and I realized that if n is huge, then it's always possible, right? And you can just show that by pigeonhole principle, where, for example, let's say you don't even need n to be that big. Let's say n is 50, right? For 2 to the 50, that is the number of different subsets we can have. Oh, and one other thing I should mention. The goal here really, we don't have to worry about this not sharing thing, because we just want to find 2 different subsets of these GIFs that have an equal sum. And if we have any overlap, that's fine in the 2 subsets, because we'll just remove them from both. So to give an example, if on one side we have 324, which has a sum of 9, and then on the other side we have 4, 5, which also has a sum of 9, then we've solved the problem, because even though we have overlap with 324 and 4, 5, we just throw out the overlap. So then we end up with 3, 2 here, and then 5. And so that's our solution. So yeah, so the goal is really just to find any 2 subsets that are different but have the same sum. And if n is at least 50, then what happens is 2 to the 50, this is the number of subsets, right? And that's quite a huge number. Meanwhile, the range of possible sums is going to be between 1 and n times the max AI. So the max sum we have here is going to be 50 times 28. And this is much smaller than this. So just by pigeonhole principle, there's definitely a solution when n equals 50. You can kind of keep searching for like how big n can we get and still get a solution. We just want this to be at least 1, right? So when n is 40, we still have a lot of solutions. Even 35, we definitely have solutions. And so it turns out we can go down to 32, and we can say that when n is 32, we definitely have a solution. And in fact, we have a lot of solutions because there's a lot of pigeonholes going on here. But below that, it's a little bit trickier. It turns out that it's definitely possible not to have a solution for 27. What we can do is do 1, 2, 4, 8, 16, and so on, all the way to 2 to the 26, which is about I guess we don't have to worry about we can just find exactly. It's about 67 million. So that is the biggest power of 2 we can fit in the constraints. And yeah, definitely no 2 subsets here will have the same sum, because the subsets here will just generate all of the sums between 1 and 2 to the 27 minus 1. Okay, so we've seen that for 27, it's possible for it to be a no. And then for 32 and above, it's definitely not possible for it to be a no. You can do a lot of math and try to tighten these bounds. I think it's possible to be a no for 28, and it's always yes for 31. And you can try to maybe 30, you can try to squeeze that in. The proofs for these get pretty complicated, but So I won't go into that, but basically, we can just think about solving the problem for relatively small n. It's not super small because you still need to solve around n equals 30, but that's a lot better than 10 to the 5th, right? And what you can do then is you can do this meet in the middle approach, where you just cut the list into 2 halves, and for each half we're going to generate all of the possibilities, and then we're going to try to look for what we need in the other half. And if we do that, let's say for n equals 30, we cut into 2 halves, then it turns out for each side we just have 3 to the 15 possibilities for kind of the number of ways to basically we're deciding for each half, for each of the gifts, whether it goes to A, whether it goes to B, or whether it goes to charity. And that's why it's 3 to the 15th. So this is the number of possibilities on each side, about 14 million. We just generate for that, for each side we generate that, and then we're looking for like the same difference across. So that's what the code here does. I have a bunch of stuff here to optimize the constant factor, like hash tables, radix sort, and so on. But yeah, basically this is the code to generate the subsets for each half, and then we just check for a solution within each subset, or within each half, first, and that helps us kind of cover a corner case where we're trying to match 0 to 0. So now we can throw out the zeros from the halves. Then I just do a radix sort and look for equal differences, which gives us an immediate solution. And so I was actually able to optimize this enough that I could do meet in the middle for 31 or below. And then I didn't actually need to do this here. I think you can just always do this meet in the middle for maybe even for 30 would probably be fine. But what I actually did here was for large n, another thing you can do is you can do a birthday attack on the sums. So in particular, if let's say n is big, so let's just cut n down to 40. Let's throw out everything except the first 40 values. And now we have this case where, again, like we were saying, the sums max out at 40 times 1e8, and meanwhile there are 2 to the 40 subsets. So what that means is if we make a frequency table of how often each sum occurs, then on average each sum will occur this many times, which means basically it means that the worst case we can approximate it as being uniformly distributed across the sums. And in that case, since there's only this many different sums and we're just looking for a pair of equal ones, that'll take about, via birthday attack, that'll take about this much time, which is not a lot of iterations. So I just generate random bit masks and then go through, take that sum. If that sum is already in my map, then I found an answer. Otherwise I just keep going. And I actually think, this part should never occur if we get here, because we covered the smaller n with meet mid. The first mission I did, I didn't code the meet mid yet. I just had I essentially had this, and I just tried this approach. And I knew it probably wasn't good, but just figured I might as well submit it and see what happens. So I got wrong answer with that. And then adding the meet mid got me to AC. Okay, so that's all of the problems for the div 2. So we covered the div 3 and the div 2. So pretty solid problems. Unfortunately, a lot of just server issues with CodeChef. Hopefully they start to figure things out soon. But anyway, that's going to be it for this video. So I'll see you in the next one.